Hello, everyone, and welcome to the DB Mastery Series, Postgres on Kubernetes edition. My name is Alicja Kucharczyk, and in this session, I will talk about HugePages for Postgres, what they are, how to size them, and when they help. HugePages are one of those settings that many Postgres users hear about, but often postpone. They may seem too operating system specific or too low level, but on larger Postgres servers, especially with large shared buffers, they can reduce memory management overhead and make memory management more predictable. I hope that after this talk, at least some of you will feel more confident deciding whether HugePages make sense for your Postgres servers or maybe not, and how to configure them properly. Before we start, a couple words about me. I'm working with Postgres for over 14 years now. Currently, I'm Postgres consulting lead at Clouds on Mars. I'm also former Microsoft Global Black Belt and later program manager for Azure Database for Postgres Flexible Server, and also organizing a Warsaw Postgres users group. Okay. The practical part of this talk is mainly focused on Linux-based Postgres deployments, especially virtual machines and bare metal servers, where you control both Postgres and the operating system. If you use managed Postgres service such as RDS, Aurora, or Azure Database for Postgres Flexible Server, you may not manage HugePages directly. But the first part of the talk should still be useful because it explains what problem HugePages solve and why they can matter for database performance. Since this is a short talk, I will intentionally simplify some kernel level details. The goal is not to turn this into deep dive into Linux memory management. The goal is to give you practical understanding that helps you configure, size, and validate HugePages on your own Postgres servers. Most examples will assume dedicated Postgres server. So if you run multiple Postgres instances or other memory-heavy application on the same machine, the same principles apply, but the sizing requires a bit more care. Before we go into the sizing, we need to make one important distinction. HugePages are not the same thing as transparent HugePages. In this talk, when I say HugePages, I mean explicit, static, or persistent HugePages. These are configured at the operating system level and then used by Postgres for shared memory. Transparent HugePages, or THP, are totally different. They are an automatic kernel mechanism. They can affect database performance for sure. And a lot of benchmark shows more likely negatively than positively. But they are not the main topic today. So for the rest of this talk, when I say HugePages, I mean those persistent HugePages. So what are persistent HugePages? To answer that, we first need to connect Postgres memory with operating system memory. Most Postgres users are aware that Postgres stores table data and index data in 8K blocks on disk and also uses 8K buffers in shared buffers. But when Postgres starts and allocates shared buffers, it does not allocate this memory directly from physical RAM. Instead, it asks the operating system to allocate the shared memory it needs. On a typical Linux system, the default memory page size is 4K. So this is the middle layer you see on the slide. So we can say that one 8K buffer in shared buffer is backed by two operating system memory pages, each 4K in the size. And this is exactly the layer where HugePages do work. Now, let's look at what happens between virtual memory and physical memory. Here, when I say virtual memory, I mean the address space used by the process. This is not a virtual machine. It's the memory abstraction provided by the operating system. Postgres works with virtual addresses. Physical RAM has physical addresses. So the CPU and the operating system needs a way to translate one into the other. The translation is stored in page tables. Conceptually, the page table tells the system this virtual memory page corresponds to this physical page in RAM. But checking the page tables for every and each memory access would be very expensive. So CPU has this small, very fast cache for address translations. This cache is called TLB, the translation look-aside buffer. So I know that many of you that come from database system like C translation and want to say transaction, but this is TLB, means translation look-aside buffer, not transaction. If the translation is already in the TLB, we have a TLB hit and the access is fast. If the translation is not there, we have a TLB miss, then the CPU needs to walk the page tables and find the correct mapping. And this is more expensive. So the important idea is this: the more pages we have, the more mappings we need, and the more pressure we put on the TLB. So huge pages reduce the number of pages. Fewer pages means fewer mappings, this translations, and fewer mappings mean less TLB pressure. Let's make this concrete with an example. Imagine we've got a server with shared buffers set to 128 gigs. If this memory is backed by default 4K pages, we need around 33 million operating system pages. That means around 33 million address translations that the system may need to manage. Now compare that with 2 megabytes HugePages. With 2 megabytes pages, the same 128 gigs of memory needs only around 65,000 of pages. So we go from about 33 million to about 65,000 mappings. That is 512 less entries. And this is the main performance argument for HugePages. Fewer page table entries, less TLB pressure, fewer expensive page table walks, and less CPU overhead. Again, HugePages do not make Postgres buffers larger. The size still remains the same. We still talk about 128 gigs of shared buffers, right? But this memory is backed by pages from the operating system that differ in size. So we've got much less translations to manage. So let's try to put this all together. What are HugePages? So HugePages are memory pages larger than the standard 4K base pages. Most commonly on typical Intel and AMD servers, this means 2 megabytes pages. The exact huge page size depends on the CPU architecture and on what the operating system supports on this particular architecture. So, although huge pages are memory feature, are not related to the physical RAM modules in the server. It's about CPU architecture and about operating system, and more to be more precise, what operating system does support on this particular architecture. So on most Intel and AMD system, you will see 2 megabytes HugePages. On other architectures, the size can be different, so the safest way to check is to look at what the operating system reports. HugePages are also an operating system feature, not a Postgres specific feature. Postgres can use them, actually can use them for years now and benefit from them, especially on large servers with large shared buffers, but they are not configured and provided by Postgres. They are configured and provided by the operating system. And the important point is that HugePages do not change Postgres internal sizes. They do not change Postgres 8K page size. They do not change Postgres 8K buffer size. They change only the size of the operating system memory pages backing Postgres shared memory. So what are the main benefits of HugePages? One big benefit is that once you configure HugePages, Postgres shared memory is backed by HugePages that stay in RAM. In practice, HugePages are not swappable. So this prevents Postgres shared buffers from being paged out under memory pressure. With normal small pages, shared memory can be paged out if the system is under heavy memory pressure and swap is enabled, of course. With HugePages, this behavior changes because HugePages are reserved and kept in memory. Another benefit is reduced CPU overhead for memory management. Because we have fewer memory pages, we also have fewer page tables entries to manage. That means less page table overhead and less pressure on this small cache called TLB. So instead of managing millions of small page mappings, the system can manage a much smaller number of large mappings. This usually means fewer expensive page table walks and less CPU overhead. HugePages can also improve memory management efficiency on systems with large amounts of RAM, especially when Postgres uses large shared memory area. For example, when shared buffers is large. If your Postgres server is small and shared buffer is small, HugePages may not make noticeable difference. But on larger dedicated Postgres servers, especially with large shared buffers, they are definitely worth understanding and considering. Now we know what HugePages are, so we can go to the sizing. The first step is to set all Postgres parameters that you want to change first. Not every Postgres parameter changes the amount of shared memory that Postgres needs, but some of them do. And the list is quite long. And I don't want to go also through all of those parameters in here. Most important one is for sure shared buffers. This is normally the biggest part of your Postgres shared memory area. So before you calculate HugePages, make sure that you already set your parameters to the values you actually want to use, and then act accordingly with the procedure to recalculate HugePages amount you need, and probably with the script that would automate setting of the HugePages number you need. Step 2 is to verify kernel HugePages support. And to be very honest with you, I included this slide mainly for completeness. On most modern Linux systems, HugePages support will already be enabled in the kernel. But if you want to check it, you can run this command and look for the HugeTLB options. But I can bet you will not need to change anything in the kernel. In most of the machines, you will have it enabled. Step 3 is to verify the HugePages size on your system. And this is important because the size can depend on the CPU architecture and the operating system. But in the majority of cases, especially on the Intel and AMD servers, you will probably see 2 megabytes HugePages. But it's better not to assume just to check it. You can verify this with this grep from protsmem.info. And this is an example output you might get, which means you've got 2 megabytes of a 2 megabytes size of a HugePage. This value is important because later we divide the required Postgres shared memory by the HugePage size. So we definitely need this. Step 4, this is something that is easy to miss, and you probably have hit this problem in the past multiple times, especially when you used pgdump and you tried to do the dump with the binary that is older than your server. Then you would have this error saying that dump cannot be done, right? Because the version, there is version mismatch. In case of HugePages, you will not see such an explicit error message. You will see, as in the slide, this weird configuration parameters error, but this basically means that your Postgres binary is in wrong version. You should always use the binary in the same version as your server. So if you've got a server in version 18, you should use binary also in version 18. Stop Postgres. The instance must be stopped. If the instance is still running, you will get an error like this, saying that postmaster PID already exists. This basically means Postgres is already running in this data directory. So before running the sizing command, stop the cluster first, whatever you use, either systemd or pgctl, just stop Postgres. Step 6, you need to use the right user. You will not be able to check the number of HugePages needed from root account. You need to switch to your instance owner, which is usually Postgres user. It might be some different one, but usually it will be Postgres user, and use this account to change the to check the number of HugePages. And now we finally get to the main command. This command tells us how many HugePages Postgres needs for this particular instance with this particular settings. Remember to use the matching Postgres binary, point it to your data directory with this -d pgdata, and then the command is -c shared memory size in HugePages. The output is just a number. For example, if the output is 75, it means that this Postgres instance needs 75 HugePages based on its current configuration and the HugePages size on the system. This is the number we'll use in the operating system configuration. There is one extra note for Debian-like systems like Ubuntu, for instance, because Debian and Ubuntu often splits the configuration file with the data directory. So put those in different directories. So then we need to modify this command a little bit. Instead of -d pgdata, you should use the config file option and direct to your Postgres conf file. And in the Postgres conf file, you will also have your pgdata location specified. So that's why you don't need to specify -d. So on Debian systems, just switch -d with the config file and you should be fine. Step 8, configure HugePages persistently. Now we need to switch from the Postgres user or whatever owner of the instance you use to root, because this part changes the operating system configuration. If Postgres told us that it needs 75 HugePages, we can configure that number with vm.number HugePages. My favorite way is to create a sysctl configuration file like shown in the slide. And then you need to apply this change with sysctl --system, which will reload all the system settings. And after that, we need to verify the settings again with grep HugePages from prodsmem info. This makes the settings persistent. meaning it will survive reboot. And this might not always succeed because if your machine is already running for quite a while, you might not be able to allocate continuous memory area to allocate for HugePages. Then unfortunately, it means you need to do reboot of the machine. And after that, your allocation should be successful. And finally, in the step 9, if everything is okay on the operating system level, so meaning you successfully allocated that many HugePages you need, then you can finally enable it in Postgres. I would recommend using a HugePages set to on. There's also try option, but on is, in my opinion, much better because you will have an information immediately if this failed or not. If you would have try, you might end up in the situation when there is not enough HugePages in the system. So Postgres would fail back to the normal small 4K pages, and you will not be informed about that. If you've got HugePages to on, then you immediately will know if HugePages were allocated successfully or not. Because if there was a problem, there's been not enough HugePages set in the system, then Postgres will simply refuse to start. We've got Postgres instance down, right? Because we needed to put it down to calculate the number of HugePages we need. So now we need to start Postgres. And with HugePages setting set to on in Postgres, if your Postgres starts successfully, it means everything went well. So you are able to set your HugePages to be used by Postgres. But still, you should verify if the number of HugePages were allocated properly. With the HugePages set to on, for sure, like there is enough of HugePages in the system, but it might be the case you've got too many, which means you will be wasting this memory because Postgres will not use HugePages for anything else than shared memory area. So you still should verify again with the same command, which is grab HugePages from prods meminfo. And this is an example output. What we see here, it's HugePages total 75, so that much as we said in the configuration file in the sysctl. Then we see HugePages free is 65. So 75 minus 65 means only 10 are actively used now, but all the free HugePages are reserved, meaning they will be used in future by Postgres. So it looks really good. It's very close fit, so we feel confident about that. And this is a pretty cool graphic generated by Notebook LLM. It's correct. So if you want like a short guide how to set HugePages, this is step-by-step approach. I want to show you benchmark results done on the machine with 32 gigabytes of RAM and 8 vCores against Postgres 18. The benchmarks were done with the internal tool used at Clouds on Mars for benchmarking. The tool is actually written on top of classic tool, which is pgbench, but is eliminating most of the systematic errors that you might hit when using just pgbench from the command line. What you can see in here for this particular machine, for this particular workload, which was TPC-B-like, so the default pgbench test, HugePages actually do not help with the performance. As you see, whatever actually connection count I would choose, I tested 3 values, and whatever database size I would choose, the HugePages off settings is actually more performant than the HugePages on setting. You will be able to see this yourself soon. We are going to make public these benchmark results, so you will be able to compare. It doesn't mean that HugePages do not make sense, but for some workloads, for some shared buffer sizes and machine, they will simply not give you the performance gain. They will give you it on much bigger shared buffer sizes on much bigger machines. Before we finish, let's quickly recap the most important takeaways. Any change to shared memory related settings may require recalculating HugePages. So it would be really good if you would have a process and script in place that in case you change actually any configuration parameter, you would recalculate, recheck if the number of HugePages required for your Postgres has not changed. Avoid both undersizing and oversizing the HugePages pool, because actually in both cases, it means wasting memory. That cannot be used for anything else. It will not be used for sorting, for anything that Workmem, for instance, is doing. With the undersizing and HugePages set to on in your PostgreSQL file, you might be a bit more secure because Postgres will simply refuse to start. But if you oversize the HugePages pool, then also it might mean memory wasting. So always remember to do this grep from prodsmeminfo to check if you have not oversized your HugePages pool needed for your Postgres server. And good news here is that allocating new HugePages might be difficult because it might require restart, but lowering the number is dynamic operation, so you don't need reboot, and it will work on the running Postgres instance. On managed services like Amazon RDS, Azure Database for Postgres, or others, this is usually handled for you. So it's good to understand why the HugePages might help you, but you usually just have simple switch to make it on or off. So you don't size and you don't configure that yourself. Okay, that's it. Thank you. If you would have any questions regarding HugePages or maybe other performance topics, please ping me on LinkedIn. Thank you a lot.